Okay, so Martina will first present the status and scientific goals of origin and HSTDM. Yeah.
Yes. Thank you very much for inviting me and giving me the opportunity to talk about these two missions. Sorry. So I'm going to talk about two very different missions. I'm going to talk about HSTDM, and I'm going to talk about the Origin Space Telescope, which will be the major part of the talk. And then at the end, I'd like to get your input for community input for HERO Origins or future far infrared satellite, which you can give me at the end later. So let's start with the high sensitivity terahertz detection module. It's actually initiated by Purple Mountains Observatory and Zheng Zai Shi, who want, and with a partner of Lerma. The idea is that at the Chinese space station, they want to fly close to it, a telescope with a 2-meter mirror. And on that telescope, they will put different instruments, including one module, this HSTDM module, which has two different heterodyne receivers, one SIS receiver going from 410 to 510 gigahertz, and another Schottky receiver going from 520 to 630 gigahertz, which will be, well, the idea is that one of them is provided by PMO and the other, at least modules, parts of it by Lerma. What do you want to do with these two receivers? The science case is to observe in astronomy, to observe atomic carbon and the evolution of carbon. At the higher frequencies, you can observe the ground state of the waterline of water, ammoniac and CH. Those will mainly be looked at in shocks and PDRs and dense cores. For the water, we would also like to look at the water trail of how it actually migrates from clouds over cores and disks to planetary systems and the origins of the solar system material. So this is one aspect of the receiver. It will also look in the opposite direction on the Earth's atmosphere and look at the 3-dimensional water vapor distribution in the stratosphere and at gases tracing the processes in the middle and upper atmosphere, including the feedback on greenhouse gases. So the receivers will be heterodyne receivers. I'm not going to give an introduction to heterodyne. In this case, the critical element is always a local oscillator and the mixer. So for the Chinese mixer, they will use an niobium nitride SiX mixer, which has the advantage of being operational also at slightly higher temperatures. Usually we operate these receivers at 4.5 Kelvin. This one you can operate at 8 to 10 Kelvin. That's important because that allows the Chinese to use their own cryocoolers, which they've developed in China for the space application. The other instrument will have Schottky mixers, which in principle don't require any cooling. They get better when you cool them, but they work at all temperatures. And an LO. And actually, we will exploit the development which has taken place for the JUICE mission on the Schottky mixers. And we propose something similar. So what is the status of HSTDM? In China, it's advancing very nicely and prototypes are being built. We have asked for APR funding at the CNES, but are waiting. A delivery is already expected next year for launch maybe as early as 2023. So now I'm going to change topics, so to speak. I'm going to talk to you about the Origin Space Telescope. That is a large mission initiated by NASA. It's a study at the moment with a large community. Here you see some of us, about 100 astronomers and NASA engineers and companies as well taking part. And the community study chairs were Asanta Corey and Margaret Meixner. To put it into context, you probably already know, NASA has actually commissioned 4 different studies of large missions, which have been submitted to the decadal review. And the decadal review is going to prioritize these missions and recommend one of them to be built and launched in the mid-late 2030s. So besides Origins, which is a file which I'm going to talk about, there's Lynx, which is an X-ray satellite. Then you have Habix, which is a satellite specifically built to look at exoplanets. It will actually fly a humongous, 70-meter star shield, so to block the central star and to be able to look at the exoplanets. And then we've heard, I think 2 or 3 days ago, also about LUVA, which is an optical UV telescope, a large optical UV telescope. So here on Origins, I will start with the science cases and the motivation. So we are asking basically 3 questions for 3 big science cases, and then there will be open science as well. How does the universe work? To answer this question, we want to look at the evolution of galaxies from cosmic time of Z about 8 to our times. You want to look at AGN. Well, obviously in the infrared, you mainly look at gas and dust. You're looking at AGN, at outflows of cooling flows coming back, at star formation. And there has been a lot of work, as you know, or you're probably involved in this with ALMA already, which is, well, 30 gigahertz soon to a terahertz, where you can trace actually all these different lines. Some of the lines, the major cooling lines, you can only get at redshifts, for example, the C+ line. And then there will be the JWST. We've learned that it will be launched on the 18th of December this year, I think. So that will take the shorter wavelength regime. But in order to really compare the evolution of these spectra and of these tracers, of these molecular lines over time, you would also like to look at them at each epoch, even if they're redshifted. So you really need to fill the gap between ALMA and the JWST. So you need a far infrared observatory, which can do that. And then you can trace these galaxies over the evolution of time and look what processes are taking place and whether any of them taking place more. So the next question is, how did we get here? In this question, we actually concentrate on the question of water, because it is believed that we need certainly water for life on Earth, and it's believed that you need water for any life. So the question is, how did we get water on Earth, and how would you get water on any other planet? So we're looking at water is already present in the interstellar medium. It will be in the clouds around protostars. It will then condense out onto protoplanetary nebula, where you have the disk of gas with the water. The star will heat, so you'll have hotter water more in the center. And in the mid-plane, where it's quite well shielded, the water will freeze out and become water ice. And then the debris disk, lots of the water can get destroyed close to the star. So in the case of our Earth, we believe that all the water was destroyed on our Earth, and we actually were resupplied with it from comets from the outer solar system. So I'm spending a little bit more time on this water question because I think that's most applicable to PCMI. What we want to look at is here the amount of water and the distribution at the different stages of the stellar evolution and the planet formation. What you have on this graph is on the y-axis, you have the water content as measured in Earth's oceans. And on the x-axis, you have a kind of the evolution time at the end comets. The purple rectangulars give you a range of amounts of waters you might expect to find. And the symbol, which looks a bit like an atom and a galaxy mixed together, is a sensitivity of origins. And what you should see from that the symbol is nearly always at the bottom of this rectangle of the expected amount of water. So in other words, origins will be able to detect water in different protostars and disk and so on. So it will be very sensitive and more sensitive than anything before. If you now look at the water lines, obviously many water lines, origins will be able to see a lot of these water lines. In contrast to ALMA, which sees the cooler lines and also is, of course, hampered by the Earth's atmosphere, which has water itself and absorbs the water emission. And the JWST with the shorter wavelengths, which will mainly have some lines which are tracing the hotter environments. JWST has the advantage of also being able to see ice. So I couldn't help myself. I'd like to show you this very nice movie which Klaus Pontoppidan has done. It mainly shows, because with origins, we will see the protoplanetary disk in one beam. So we'll see all these water lines at once. It's getting complicated. But if we do high spectral resolution, we see the spectrum. Here you have a line which is close to the star. It's a warm line with the red and the blue shifted part. Here you have a line coming from a region further out, where the double peak is closer together because relative velocities are closer to the velocity of the disk. And now there will be the ground line of water out here. And as this cursor goes, this is where the water is in the disk. And now he's going to tip the disk and see how the spectra will change. So that's where the emission is coming from. And then he'll tip it to a kind of face on when you don't see the double peak anymore, and he'll tip it back. So it's actually, I like it very much. It's a nice movie they've done. So the take-home message is from that, even if you don't have the spatial resolution, if you have the spectral resolution, you can actually do a lot with it together with a simple model of a disk. You can look at the spectra and see, well, maybe one peak is higher than the other, so you know that more water is on the left than on the right. So you can do the line tomography. You get a lot of information back if you have high spectral resolution receivers. And we come back to that when we come to the heterodyne, of course. Oops. So the other thing, now you've measured the water, you know where the water is, you know what temperature the water has in the disk. Now you want to measure maybe the mass of the disk as well to put it in context. Ideally, we would like to measure it in H2. HT doesn't have a dipole moment, as everybody knows, so it doesn't have emission at this low temperatures. So then what we do usually is we observe CO. CO could be optically thick. It also requires a conversion factor from CO to H2, which is not that well known. So the better thing would be to measure HD. So Origin is going to measure, kind of weigh the disk in HD by looking at the HD 1 to 0 transition. So the third question, the third major science of Origins is, are we alone? So here we are going to look at the transit of exoplanets around M and K stars. And we're looking at the molecules in the atmosphere of these exoplanets. And we're going to look at biotracers, which are elements which are considered necessary to have life, but that doesn't mean there is life. And then at biosignatures, which are molecular combination of molecules, which would actually react and disappear unless they are replenished in the atmosphere by what we think life could only do. So if you find these biosignatures, you know that it's a chemical equilibrium which has to be replenished so that there might be life. And the hope is that a few of these biosignatures could be found on a few of these exoplanets. And if they are not found, that will be a significant statement as well. Okay, we want to do all this great stuff, so we need a telescope to go with it, a satellite. So here's the Origin Space Telescope. It's a mid to far infrared satellite covering a wavelength range of 2.8 to 588 microns. It has a large, well, at least by space standard, large telescope of 5.9 meters. Which is actually the same collecting area as the JWST. It's diffraction limited to 30 microns, but more importantly, it's actually cooled to 4.5 Kelvin. And I'll come back to that as well. It's cooled not with cryogenic gases which evaporate, but with cryocoolers. It's agile, so it'll do 60 arc seconds per second. It will require a large launch vehicle with a payload of 7.5 to 10 meter payload, but there are several being developed as we speak. So we we hope that one of them will be ready. It'll carry propellant for at least a 10-year mission, and it will be serviceable. Of course, with the cooling, it works until the cryocoolers don't work anymore or break down. It'll be an L2 orbit, and it is a Spitzer-like design with minimum deployment. So it's kind of should be relatively safe in that it should work. So why do we want to go to 4.5 Kelvin? So here's a graph which shows you the background of astronomical background and the telescope background together as a function of wavelengths. So the astronomical background is this dark red line here. And then the telescope background are for telescopes at different temperatures. So what you can see immediately, if you don't need the far infrared, if you go to mid-infrared, you'll be perfectly fine with the telescope cooled to 80 or 40 Kelvin. But if you want to go to the far infrared with bolometer detectors, you really have an interest to cool your telescope more. And if you want to be limited for the astronomical background, you'd like to cool it down to 4.5 Kelvin, which is what we anticipate. And here you have some prior missions with Myriad JWST, with the cooling of, I think that's 30 or 40 Kelvin, which is perfectly sufficient, and then other former missions. And if you now take the workhorse kind of receiver of origins, as it explains the origins spectrometer surveyor, you actually get an increase in sensitivity of a factor of 1,000. So that means your integration time is diminished by a factor of 1,000,000. So that kind of opens a completely different case in science. Cooling the telescope obviously is not enough. You need to have the instrument to go with it. So Origins has 3 baseline instruments. So Origins survey spectrometers, which covers a wide wavelength range from 25 to 588 microns and comes in kind of 3 different resolution settings. One is a resolution of 300, another of 43,000, and for a limited range, including the HD line, it will go up to a resolution of 325,000. At least that's the hope. By putting respective optics in front of it. So you put a grating, FTS, and a Fabry-Perot to get to this very high one. Then there is a FIP, far infrared imager polarimeter. This is actually built to do sensitive surveys quickly and to polarimetry. It's made for maps and imaging. It'll come in 2 different frequency regimes, 50 and 250 microns. And the third instrument is a dedicated mid-infrared transit camera, spectrometer camera transit, designed largely by the Japanese, which has a limited frequency, about mid-infrared, 2.8, 200 micron. But what is important about this instrument, it's built to be ultra stable, because you want to integrate down the constituents of the atmosphere of these exoplanets. So it's built for that. Then there are 2 upgate instruments. That is, if we find enough money, we want to put these instruments on it too. There's a heterodyne receiver for Origins. I have 1 extra slide for that one, because I've been involved in that. And then there's a mid-infrared wild field imager, which has a field of 3 by 3 arc minutes in the same mid-infrared wavelengths of 5 to 28 micron and a resolution of 5 to 300. So the heterodyne array receiver for Origins is the first heterodyne array receiver, which is designed for a satellite mission. We had a very nice talk by Christoph Riesacher 2 days ago about heterodyne array receivers. It's built around the water case. So when we want to have this very high spectral resolution and observe the water lines, so we need the high spectral resolution. It's easy for heterodyne receivers, so 10 to the 6, 10 to 7. In the lab, we've gone to 10 to the 10, but nobody wants it because you have not enough photons anymore. In astronomy, it's not very useful, but that's kind of not a problem. We want to see lots of the different water lines. So we want to span a frequency range of 486 to 2,700 gigahertz continuously. The IF bandwidth, which is the instantaneous bandwidth you can look at, is at least 6, if not 8 gigahertz. Because it's a water case and we're looking mainly at protoplanets and disk, we actually don't need a very big array. So we think that an array of 3 by 3 pixels should be enough. For sensitivity, we want to observe the two polarizations, and we put dual frequency in it as well. So the instrument is, we kind of looked at all the other heterodyne instruments and learned, saw what we can learn. It's a standard instrument where, and the heterodyne, where I need a stick, where you take the signal from the sky and you mix it with an artificial signal, monochromatic signal, which you produce in the spacecraft. You overlay the two, you mix it. That means you create the beat frequency. The beating signal contains all the information from the sky, but is at much lower frequency of only a few gigahertz, which you then easily can amplify and detect relatively easily. The tricky bit of this instrument, that's standard, the tricky bit is that the satellite gives us some constraints. And the trickiest of those is that we have very limited cooling power here at 4 Kelvin or 4.5 Kelvin. We have 100 milliwatts for all of the instruments. To give you a kind of a reference, if I go and buy a cryostat of a catalog, I'll have either 500 or 1,000. That's the standard. Here we have 100 for all 4 instruments. So we thought we could take about 30 or 40 for the heterodyne instrument. So now we can't use our normal first state amplifiers anymore because they take too much energy. So we have to go to special components. So low noise amplifiers with very little power consumption. And the same is true. The other critical bit is the back end. We have to have very low power consuming back end. So we looked around what is available and selected some components which are looking very promising for this mission. And the other thing is to save a bit on mass and volume. We decided that all this frequency range we will only cover with 4 bands. I think Herschel had 7 and a smaller frequency range, so we want to be very wide band. Good. How does the heterodyne, how do the origins instrument, look with respect to each other? Here you have the spectral resolving power in comparison to wavelengths with the mid-infrared instrument here, the fast camera for large mapping here, the OSS with its three spectral resolution powers, and then the heterodyne instrument for the very highest spectral resolution images. How does it look with respect to other instruments, previous or planned? Here we have 1 hour sensitivity as a function of wavelengths. Origins OSS you've already seen, and the heterodyne receiver is placed in here, which gives you about an order of magnitude improvement as compared to the Herschel instrument. Good. Where are we now? Well, we've submitted it to the decadal review, and we are waiting anxiously the decision, which was supposed to have already taken place, but we are sure it's still, well, we are told it's still in autumn, it could be any day now, which one of the 4 missions they would recommend to be built and go ahead. In parallel, we have prepared, we have submitted a Voyage 2050 proposal for Origins and Hero with it. So because ESA has already said that whatever NASA chooses, they want to contribute at the level of an M mission to that large mission. For France, we have submitted an APR proposal, currently have 10 laboratories on it. And at the moment, we have a French instrument lead. So now I'm coming to the third part of the talk, which is kind of soliciting you. For the RPR proposal, we kind of want to prepare Hero and Origins in case it gets selected. So I want to reach out to you. We've started, but I haven't reached everybody yet to contact French laboratories who might be interested. And we want to organize a science workshop to look at the science again from a more European point of view. I mean, obviously science isn't different, but maybe the European interests are different, which I ideally wanted to organize still at the end of this year. And then we have to get together a technical consortium. I'm thinking here more European, here as well, or European. And then adapt Hero and if you want a heterodyne instrument, if that's the outcome of the further first two phases, which I hope, and organize. So for the science workshop, very good. Anybody interested to help me organize it or participate, please come up to me. I'm thinking of a workshop focused on Europe, but also inviting, of course, international people and probably just here in Paris. Here's a list of laboratories we've reached out to when we submitted the APR proposal and who have said yes, at least one person has said they. So if you're not here on the list, please come and join if you're interested. And that's actually the end of my talk. So I leave you with a little bit of literature on origins. There is a mission concept study report, which I had in my backpack, but took out this morning because it's heavy and thick. The web pages which have it on it. There's also lots of white paper in the US. There's a Voyage white paper. There's the Yatis paper series. There's lots of reading you can do if you want. Or you can contact me and I tell you what I know. Thank you.
Perfectly on time. So we have questions. Jérôme first.
Yes, I didn't understand what it means to be serviceable.
But in principle,
because this is an L2 point, so it's not closed.
No, but in principle, you could fly. So what we looked at it only kind of a little bit, because that was one of the inputs. We want to be able, for example, to dismount any of the instruments without disturbing the rest. So be able, for example, to dismount any of the instruments out of the telescope without having to deassemble the whole telescope, right? And in principle,
why do you want this? The question. Robots.
Well, the idea was to have it sort of like the Hubble Space Telescope, to refuel it. If you just need propellants, if the cryocoolers still work, you could go on and refuel it.
But
you could change instruments.
It's better to launch another one then?
Maybe. I mean, that was not the focus of the study to be serviceable. It was a side aspect we looked at, and we decided to do these two aspects, that you could get any instrument out. And
Mark, you want to say a word also on that?
Yeah, I really wonder whether it's a safe bet regarding the complexity it introduces to be able to extract the instrument without affecting the telescope. It means something also on how it is conceived and how it's going to be assembled on the ground. So I think unless it is critical to be able to do it, I'm not sure it's a good strategic choice, because if we fly a tag on the mission, which is ultra complex, high risk,
it wasn't one of the focus of the study. We spent, I don't know, a few hours on it and said, okay.
I had no idea where
it was another request.
So maybe we'll take some questions online from Christophe about another subject.
Okay, thank you. Nice talk, Martina. If you go back to the slide where you compare the performance of the Origins instrument compared to this one, yeah. I don't know if you have done it, but what would it give if you compare to the Hermes instrument on Sophia that is currently paused, but might be revived at some point?
I don't know exactly what height it has on this plot. I mean, we looked at, a comparison to Sophia. The big advantage Origins has, it's cooled. The dish is actually cooled, so that makes a lot of advantage for the bolometer arrays, kind of, which Hermes is also. And the dish is much bigger. And you do still have, for example, for the water case, it's actually surprisingly that even at this altitude where Sophia flies, you still have remnant water lines which kind of mask, and ozone lines which kind of mask not much of the spectrum, but sometimes a relevant part. But it's a point taken, I should see where Hermes goes on this sensitivity graph.
Yeah, just for curiosity, it would be nice to see if it's 1 or 2 orders of magnitude worse. Yeah. Thank you.
Okay. Okay. Thank you again, Martina.